Good morning, class. My name is Gabriela. I used to be a former student here like about 2 years ago. I finished. Your teacher has asked me to come and speak to you about mass and motion and how it all works when it's going down an incline. So we're going to be looking at that today. So our lab started by a group of friends that went to a roller coaster during the day when there were so many people at Valley Fair, that is. So they were going down the hill and the roller coaster, everything. And so at the end of the day, they were like they wanted to go for a couple of rides, but there weren't that many people. So they're like, oh, will it go down faster or will it go down slower? Because there's like less people, meaning less mass. So our group tried to answer that question, and we predicted that the more mass there is, the faster that the roller coaster is gonna go down the hill. So at the end of the day, it might go a little bit slower. So before we get started, a couple of things that I need you to know is, or as a reminder, since you guys just covered the topic, is velocity is measured in meters per second, acceleration is in meters per second square, mass is measured in grams, position, which is also the distance, is measured in meters, and acceleration, the only equation I need you to remember for this lecture is acceleration equals to force divided by mass. Before we get started in our lab, let's look at a background information about who kind of started it and who did this kind of research before. Galileo was one of the people that did this, and he was interested in mathematics of the motion. So what he did was, when he was in house arrest during his lifetime, as you can see the picture here in the background, um, he would throw a ball down this incline and he would try to measure how fast it goes. But the problem was he didn't have all the equipment that we have now, so it was really hard for him, and the ball was just going so fast, so he couldn't like really measure it. So he had to try to figure out a way to make it go a little bit slower. So what he did was, as you can see, this little metal parts, he would throw the ball, somehow it will slow it down. So he was able to measure it, and then he had an instrument that he used to measure the time. So he did that with different masses, and he found an answer, which I'm gonna discuss it at the end of this discussion. I don't want to give out what we came up with. So let's look at our materials and procedures for our lab that we did. We were trying to recreate his lab, or with our new technology though. So the materials that we used was the motion detector, as you can see here, a cart with a tracks, and then different ways to add mass to the cart, and then a computer with Logger Pro program. The Logger Pro program, you can be able to manipulate it to measure anything you want. You can do position times time graph, uh, acceleration versus mass graph, anything you wanted. You can just have the graphs. Usually what you would do is you would have the position versus the time graph, and the slope would be the acceleration, and then the acceleration versus time graph too, you can do that, or you can plot an acceleration based on what you found versus the mass, what we're going to use today. So what we did was, first we weighed the cart by itself without adding any weight, which was 181 grams. So we let it go down the track, which one person started the program collecting the data, the other person stopped the cart, and the third person was just making sure everything was okay, that it wasn't falling off, and holding the motion detector so that it doesn't fall off or measure something else. So what we did was, we let it go down 3 times, and then we added mass, 50 grams on each side. So when we did that, that means we added 100 gram, and we let it go down the slide again 3 times, and then we did a third trial when we added another 100 gram, 50 gram on each side, making a total of 200 grams that we added so far, and we did the same thing. So this table shows us the measurements that we got. So you can see the mass in grams. It was 181 without the weight added, and then 281 and 381. And then here are the trials, which was the acceleration that was calculated. So as you can see, it was in meters per second squared. We measured it. So for each trial, we had to average it out. And then for the uncertainty, as we just learned it, we have to calculate or account for any uncertainty or anything that wasn't accounted for any error that could have occurred. So for the mass, it was 0.5 gram was what we saw that was like uncertainty between masses, or when you retry. So we figured we would do uncertainty zero point 0.5 grams based on that. For the acceleration, what we did was we took the highest number, subtracted it from the lowest number, and um, whatever result we got, we divided it by 2, so that became our uncertainty then for that case. So for each mass added, we did that, and you can see the results here. So based on the data and table that we got, we were able to graph it. So as you can see in the y-axis, we had the acceleration in meters per second squared, and in the x-axis, we had mass in grams. As you can see, the slope, if you just look at it without looking at the numbers here, it looks like it's like a little bit increasing. But that's actually not correct, because when we look at the slope itself, it's 0.00022 plus or minus with the uncertainty of 0.00036. So in this case, the uncertainty is more than the slope. That means that it's negligible. And when we say negligible, that means the slope could be 0 when we add the uncertainty. So that means that it didn't increase or decrease. And if we go back to the table, we can see that, like, let's say the trial number 2, let's take that. If we see it, we can see that it kept on increasing with the more mass we added, the more it increased. But this was without the uncertainty being added or subtracted to it. So if we were to add to one of them with the uncertainty, like, it will overlap with the others. So what we concluded was that mass doesn't have any effect in how fast an object goes. And this kind of comes through with our equation force equals to, or sorry, acceleration equals to force over mass. Because the force, as the mass increases, the force will increase as well. So it will kind of, the masses will kind of cancel out. So that means that acceleration is always going to be constant regardless of the mass. So that's what Galileo also discovered. And that concludes our presentation today. Any questions? Alright, and these are my bibliography. Thank you for listening, guys. Have a good day.